We are the Mathengineers. I'm Aishwarya, and I'm presenting with June and Rohan.
95% of the students at the Matheny School have speech impairments and require speech-generating devices, or SGDs. The current gold standard SGD at Matheny is the Little Mac, which is shown here. They are limited by their high cost, over $100, and are also frequently damaged by the students. This is mainly because there is no effective mounting system in place, so the students will often knock them over and damage them. Our solution to this problem is to create a mount that is compatible with the current Little Mac devices to reduce the frequency of damage. Once we do this, we also hope to redesign the SGD to be less costly and retain all the functionality of the Little Mac.
So we started with a CAD model of our mount, and its shape is designed to match the base of the Little Mac with pegs where there are holes in the device. This should prevent side-to-side movement. We realized one limitation of the design of the pegs as is, as they do not prevent an individual from picking up the device. Therefore, we are working on a new model that overcomes this problem. This base is attached to a clamp that will fasten around the wheelchair table, and a screw will fit into the clamp to tighten it as needed. And looking at the different mount designs, we were able to narrow down our choices, and we decided that the clamp would be a better choice than, for example, glue, suction cups, or Velcro. In order to account for any wheelchair trays that have a lip at the edge, the clamp also provides some extra space. In case printing in a single piece does not work, we have also created a modular design that can easily be assembled, which can be seen on the bottom left.
Our primary testing objective for this prototype was to ensure that the size measurements align with the intended specification. We wanted the design to be compatible with the Little Mac device, the universal switches used by AbleNet, and the wheelchair models in use at Matheny. When creating the design, we allowed for a little extra room, 0.025 inches, which allows for a 0.5% tolerance, but it is still a tight fit to prevent movement.
So now using our CAD model, we were able to construct a force diagram, which takes a look at where the forces and moments will be distributed across our mount. So just looking at a 2D view, when the screw is tightened, it's going to create a normal force against the bottom of the table, which will then translate to a force from the screw onto the mount itself. And that is going to create a moment at the edge of the mount, and that's going to be translated into a distributed load across the piece of the mount that's placed on the table, which creates a normal force at the center of that whole piece. Well, we can approximate it as being at the center, even though it's distributed, and that's where the actual friction is going to be created. And now if we look at what that normal force is going to be equal to, it's going to be equal to 4 inches times the force from the screw divided by 3.88 inches, which is the distance from the center of that piece across the table to the arm where the moment is gathered. And so looking at what we're going to be measuring, first we're going to take a look at opinions from the Matheny speech pathologist just to see if she's on board with our design and if there's any glaring flaws that need to be addressed. We're also going to do some quantitative measurements. So we're going to look at the maximum cutting force with deformation. We expect there to be some deformation at the corners where there's going to be moments. And so we're going to address that by using making sure that the deformation is less than 1 degree when we can achieve a force of 120 newtons. And so that should be a good target goal as something that can be tightened over and over again without causing significant damage. And then maximum tightening force upon breaking, we want this to be much higher, so around 500 newtons, and that's just so that somebody doesn't tighten it too hard and then break it, because that could cause like shattering, splinters, things like that, and obviously breaking the device. And then our force of horizontal displacement, we want it to be a minimum of 100 newtons. So this is the actual important measurement, right? It's how much force it takes to actually move the mount and device. And we want that to be at least 100 newtons, which is about 20 pounds. And that's a good target for somebody on a wheelchair to move it back and forth.
Okay, for testing, we have 3 different aspects where variables come into play. This includes a cap versus no cap for a bolt. The cap should prevent any deformation of the bolt. On the bolt, we will be using a nut. However, we will also test having a washer to increase the max force with the washer and the nut together. Finally, we will compare having silicone pads to not having them to see if this will greatly increase the force of displacement.